To perform an ANOVA, we need to make a ANOVA table. We introduce several columns: source, degrees of freedom, sum of squares, mean square, our test statistic f, and our p-value. All of these are essential to understanding different parts of our data. Our sum of squares tells us the variation of our sample means. If this is large, we already have an indication that we might have to reject our null hypothesis. The mean square is our sum of squares divided by the degrees of freedom associated with its source, otherwise indicating variance within our sample means. I have also included our null hypothesis, which indicates no variation and that all of our means are equal, and our alternative hypothesis, where at least one of our means does not equal another. One goal of performing ANOVA is to see whether or not our null hypothesis is true. Are the means we find equal to each other or close to equal? If so, then there is little to no variance. So with a two-factor ANOVA, our table is not much different. With a two-factor ANOVA, we just take into account our second factor. In addition to understanding each column with respect to each factor, we can also see the interaction of the two factors. This becomes majorly important when we want to see if two factors are related to each other. A simple example of this is if our factor A is ice cream sales and our factor B is temperature. While the temperature is up, the ice cream sales should rise as well, indicating interaction. With a two-factor ANOVA, we still have a null hypothesis, however, we just tailor it to each factor, as seen below. Let's look at this example. The data I want to do a two-factor ANOVA table for is in the gray table, where we are looking at car models and tire brands, and we want to know how long the tires last in years. Factor 1, or factor A, is our tire brand, and factor B is our car model, and we have sampled 3 random individuals for each combination. On the right is our ANOVA table. When our p-value is low, like our tire brand's p-value, where it equals 0.0001, there is what we call strong evidence against our null hypothesis, otherwise saying that there is noticeable variation within our tire brand data. Therefore, we can reject our alpha null hypothesis I have written from our last slide. Our car model's p-value is a little higher, so we know that there is less variation within our car model data, however not enough to fail to reject our null hypothesis. The larger the p-value, the weaker the evidence we have against our null hypothesis. Indicating population means whose values must be pretty close to one another.